We will find the Norton equivalent for the given circuit for terminal A and B, and we will see how the Norton circuit works basically. So in order to find Norton equivalent circuit, what I will do, I will have to short these two terminals. So these two terminals are short circuited, and I have to find the short circuit current ISC, which is IN, Norton's Norton equivalent circuits, the current, the value of the current source. So this short circuit effectively shorts out the 15 ohms resistance. So basically we are ending up having a circuit like this. I will not draw the 15 ohms because it is shorted out. So we have two parallel paths for the current source of 3 amps, and we can apply current divider rule to find the value of the short circuit current, which is the current through the 10 ohms resistance. So 3 over 5 plus 10, and since I am finding the current through the 10 ohms resistance, which is this current, I will multiply by 5. So what I get is 1 amps. So that is the value of the current source. IN is 1 amps, is equal to 1 amps. So that's there. Now I need to find the Norton equivalent resistance. So in order to do that, I will redraw the circuit here, the original circuit. So this is the one, and I need to find the resistance, the value of the resistance that is that I get from looking at these two terminals. So 15 ohms, 10 ohms and 5 ohms there. And of course I have to make the sources inactive, since there is only one source, and that's a current source. So I will have to make it an open circuit like that. So once I do that, I actually have 10 ohms and 5 ohms in series, and then the total that 15 ohms, the 5 and 10 ohm series combination is 15 ohms, that comes in parallel with this 15 ohms if the resistance is seen from here. So basically we end up having something like this, and both 15 ohms, there and there, 15 ohms. So of course the equivalent resistance will be half of that, that is 7.5 ohms, and that's the Norton resistance. So this is the circuit. Rn is 7.5 ohms. So that's there, and this is again terminal AB. So basically what we have done, this is our original circuit. So I will draw the original circuit once again just to see what we get in the end. So this is the current 3 amps, and this was our circuit, 5 ohms here, 10 ohms here, 15 ohms here, and this is terminal AB. Now this whole part is replaced by one current source of value 1 amps and a resistance of value 7.5 ohms. So this was our circuit. There was a current source of 3 amps and there is a combination of resistances. So the whole thing is replaced using Norton's theorem by just one current source and one parallel resistance. So it will give the same response here. That is, if a resistance is connected of any value in this terminal, we will get the same response. So the current, whatever it is, IAB, will be the same if this was solved by some other whatever, let's call it RL. If RL was connected here by any other method, whatever method we had used in the original circuit, we would get a value of IB, IAB, which is through the current through RL. That will be the same. It will, the current using the Norton's equivalent circuit will be the same. So basically we are replacing this whole part by this just one current source and one parallel resistance. And if the circuit is, this circuit could be even bigger, as we have seen in some examples previously. So I am just drawing these two together, these two original circuit and the equivalent circuit, just to show the comparison. So yeah.